All right, we'll get started then. Um, I know we didn't quite make it a short day on Monday, but I am hoping to kind of keep the lecture kind of short today, just because I don't know. In my opinion, we shouldn't have class on the day before Thanksgiving. I think it's awful that we do. I don't think we should have class the week before Thanksgiving or the week of Thanksgiving, but neither here nor there. I also think that fall semester deserves a spring break, but that's a completely different discussion. Uh, so a few things I want to talk about before I get started with the section, though I do hope to kind of keep it short today. I've been grading the exam threes, and I haven't got all the way through them. In fact, I don't even think I've made it halfway through the exams at this point. However, of the little bit less than half of the exams that I've looked at this point, the scores have been kind of rough. I'm trying to give a little bit more feedback on this exam because I know it was a harder exam. But I'm also thinking of how we can learn from maybe the mistakes we made on exam 3 without having the impact on the grade be as harsh. So here's kind of what I'm thinking, and maybe I can get some feedback from you guys. What I'm thinking of doing is, instead of the typical you can get 50% of your missed points back, I'm thinking of upping that to you can get 75% of your missed points back, which essentially makes it so that if you got a 50% on the test, that you could get up to like an 87.5%. If you did a 50% to begin with, and then you got 100% on the redo. So that's one thing I'm thinking of. I was also thinking of holding an additional session. Time, not sure about. Sometime next week, probably Monday or Tuesday, where anyone could come and drop in and ask questions. You could talk to your classmates. It would about the test. You shouldn't be giving out answers, but you could talk to your classmates about the process to getting the answers, and you could talk to me and ask for hints from me. I wouldn't tell you how to do the problems, but I'd be there to maybe guide the process. So that's what I'm thinking of doing, allowing a little bit more points back on exam 3 and allowing you the opportunity to talk to me and your classmates about your thought processes for exam 3. I know you guys don't know how you've done on the exam yet, obviously, because I haven't finished grading them, but does that sound like a fair plan to everybody of the 3 of you that are here? Okay. Getting some positive feedback there. Okay. All right, then that's what we'll do. I'm trying to make it my goal today to finish the exam 3s. I'm kind of letting my other classes and their grading slide a little bit, so that, I think I'll do my other classes grading for their exams next week so I can get your guys' done. No problem. I want, school shouldn't be, what is the word, punitive? I just want you guys to learn from your mistakes, learn the calculus, and move on and be good calculus students. That's all I want. So that's what we'll do. I'll finish grading these calc exams hopefully today. That's really my big goal today, but I don't want to make any promises. And then I'll give a pretty generous window for doing the remakes, but I do want those in sometime before hold on, my husband's looking. What do you want? Hold on, just a second. Let me pause and mute myself. All right, sorry about that. Oh wait, am I recording? Yes, I am. So I don't even know what I was saying. I'll get those graded. I want to get the remakes done soon because I want those in. I'm going to give you a generous timeline for them, but I want them in relatively quickly so that I can post the answer key to exam 3 as well. Because I want you to have the answer keys for all 3 exams when you go to study for the final. Now, for the final exam, I'm going to kind of cut some of the material that we've learned. So you will have material from test 1, test 2, test 3, or exam 1, exam 2, exam 3. And then you'll also have this stuff that we learned at the end. Now, I kind of want to keep it so that you're only studying the most important stuff. So I don't think I'm going to do any of the Riemann sum stuff. I think I'm just going to, I've taught you guys about it. You've seen it. Why aren't my fingers working on my screen at all? My fingers not working. I don't think I'm going to test you over any of this stuff, though, the rectangle stuff. I think I'm going to keep it mostly serious. Why are you not working? So none of this stuff here. Let's see. But really having some trouble here. Okay. What I'm going to do, I'm going to stop this recording. I'm going to plug my headset into my computer, talk a little bit while I restart my iPad, because I think my iPad just needs a reset at this point. So I'm going to stop this recording. Okay, there we go. Now we're back in business. Anyway, I don't know what I was saying before I had to restart my iPad. I think I was just saying I'm going to try to keep the Unit 4 stuff pretty minimal, and I'll make a list online of the stuff that you need to know. And I'm not going to do a comprehensive final exam review. There's a review for Exam 1, Exam 2, Exam 3, and then I will do a Unit 4 review problems, so just the Unit 4 stuff. And then for reviewing the Test 1, Test 2, Test 3 material, Exam 1, Exam 2, Exam 3 material, you can go look back at the Exam 1, Exam 2, and Exam 3 reviews. And I will have the answer keys for Exam 1, 2, and 3 available. Someone just asked, 3.7 isn't going to be on this test, just our final, correct? 3.7, so 3.7 is antiderivatives, which is basically indefinite integrals, and that's going to be on the final exam. So there's not a test 4, there's just a test 1, test 2, test 3, Exam 1, Exam 2, Exam 3, which we've already taken. And then the final exam is the last exam, and it'll have antiderivatives on it, but it's in the form of integrals. It's not in the form of saying antiderivatives. It's the same idea, but we call it integrals now. Does that make sense? It's okay. It's all right. I feel that. It's the end of the semester. Next week is our last actual week of classes, and then it is finals week. So we only have 2 lectures left after this one, and I'll do a review session as well, and then we will also do I'll do an additional session where it'll be you can come and talk about the test, about test 3, answer questions, talk to your classmates about mistakes, and we'll do that as well. And I'll compile it all into an announcement so that it's all in one place and not me rambling. So going on, actually talking about the material at hand here. This is a big section. So this is called integral substitution, but oftentimes we call this, I have to pair my pen again. Give me a moment. Oh, wait. Oh, shit. This is sorry. I'm going to start a recording, stop a recording, and then I guess pray that this doesn't corrupt itself. There we go. I'm so nervous after corrupting a 95-minute file. I'm very nervous about corrupting another file. Anyway, this is called integral substitution. We typically call this U substitution. We typically don't say integral substitution. The words we use are U substitution. That's the technique we're about to talk about. And it's to make it so that we can go a little fancier with our integration. You can go a little more pizzazz. So here's the big idea. We talked about chain rule when we talked about derivatives, and we said, hey, if you have some composition of functions, like look at this e raised to the x cubed plus 2x minus 5. We said, if you want to take the derivative of this, no big deal. You take the derivative of the exponent, and the derivative of the exponent is 3x squared plus 2, and then you would multiply it by the derivative, the e to the x cubed plus 2x minus 5. And that was your derivative. Now, what would make sense then is that there has to be an opposite direction, right? If chain rule has one direction, we should be able to go the opposite direction when we use integrals, because it's the antiderivative. And we can. So what we could say, if we know this is the derivative of this function, then we know the integral of this function would be e to the x cubed plus 2x minus 5 plus c, because this derivative is this. So there's that backwards direction that we can go there. However, getting it to go in that backwards direction is a little bit less straightforward than chain rule was. I'm not going to actually talk about this rule. I'm just going to kind of go straight into an example. So if we're looking here, you're noticing that there's like, okay, there's this function here and there's a derivative. I can look at this and I see like, oh, hey, this is the derivative of this. You start to see kind of connections like this. And you're going to want to, sorry, my dog is sneezing and distracting me. You're going to want to start making some substitutions and choices. Okay, give me a moment to collect my thoughts first, collect my words because it's coming all rambly. So, typically good choices for what you make U. Something that's inside of a radical or a large power. I don't like that color. Oops. Still don't like that color. Let's make it a little bit darker. All right, something inside a large power or inside of a radical makes a good choice for you. So if I'm looking at, where's my pointer? If I'm looking at this guy down here, I see that this guy is inside of a radical. I also see that if I took the derivative of the thing inside the radical, I get 4x minus 3, which I see on the outside. So a good choice for U here is the thing inside the radical. So U would be 2x squared minus 3x plus 5. Here, I can't FOIL this out. If this is raised to the pi power, I can't FOIL out pi. That's not a number. It's not like x. This isn't like raised to the second power, third power, fourth power. I can't do anything with this power here. So this is trapped inside of something raised to a weird power. So that tends to make a good choice for you. Additionally, if I look at this, I see that the derivative of cosine is negative sine, and I see a sine out here. So if you think about what happened out here, how the derivative ends up kind of canceling out. So you want to think about, will this derivative cancel out with something over here? The other choice, another good choice for U substitution, something in the denominator, sometimes in conjunction with option 1. So sometimes you see radicals or powers inside the denominator, but something in the denominator can make a good choice. So if I'm looking at 16b minus 4 over 4b squared minus 2b plus 3, oops, this 4b squared minus 2b plus 3 would make a good choice for you. And if you notice, the numerator here, the derivative of the denominator would be 8b minus 2, and that's double what you see up here. So you're starting to see like this, you can see sort of the derivative of this guy up in the numerator. Down here, we have a power and a denominator, so you want to kind of choose the most inside thing. Just inside the large power. If you'll notice, the numerator is the derivative of just the inside here. 3z squared right here, 4z cubed. That is the derivative of just the inside here. So z cubed plus z to the fourth would be a good choice for you. Another good choice, something inside of a function. So sort of like the same idea, like inside of parentheses, inside of a radical. Things inside of a function, like in the exponent of e, on the inside of tangent, on the inside of ln, those tend to be good choices. So I see here we have tangent, that's not my pen, we have tangent in the exponent of e. I also know that the derivative of tangent is secant squared, and I see a secant squared out here. So tangent theta would make a good choice. I'll make a note that I see the derivative of tangent. When I look at this guy, yes, there's a denominator here. So you could be like, well, should I use the denominator as the u? This just takes practice. This takes practice and learning. But the inside of sine, the inside part here, tends to be the bigger problem. If you are trapped inside of a function, that tends to be the biggest issue. So a good choice of u here would be the inside of sine. Right? The cubed root of x, which is the same thing as x raised to the 1/3. The key to success on these is you just keep trying things. You're going to try things that don't work out. You just keep trying. Because sometimes things don't work out and there's no algorithm to tell you what will always work. There really isn't. Sometimes you'll try things and it won't work, so you go back and you try something different. So I want to go through and do several examples of this. And I know we have examples on this next page here, but I kind of want to go through and actually just do some of these guys. I'm going to add a new page in. Let's see. Like that, yes. So the first one I had there, it was 4x minus 3. And then, was it the seventh root? Seventh root of 2x squared minus 3x plus 5 dx. And I had already said, one of the things we had said was that u should be the inside of the function. So one of the questions, an excellent question, one of the questions is, so is u substitution used just because it would be too difficult to integrate as is? And the answer is yes. So it's more than just being it's what you're seeing is unable to be integrated. So when you see it in this form here, we don't have any way of dealing with this that would allow us to integrate it with like our power rule. Like I can't distribute the seventh root over everything. So like there's no way for me to put like these guys in the inside of here. So oftentimes it's just that there's nothing we can do to actually combine these things together and then use the rules that we have. So it's a rule that allows us to do things that like literally could not be done without this rule. Does that make sense? Yeah, no problem. So I want to go back. Notice on this step here, I did something. I did the du dx and then I multiplied the dx over. Because this would happen every single time, we end up skipping this step. This step ends up just kind of not happening because you know that the dx is just going to end up over here on the other side. You know that's going to happen every time. So typically we go from this step here, and then this becomes a du, and you tack a dx on the side, on the end of this one. So here, I'm going to make this du, and then I'm going to take the derivative. This will be 4x minus 3, and then I'm just going to put the dx here. Technically, the dx was down here and then gets multiplied over, but that's just an additional step, and it's unnecessary for us to do that additional step there. But you're just, from this step to this step, you're just taking a derivative. So the u becomes a du, and this guy over here becomes 4x minus 3, and then a dx comes at the end. A little bit of a process that's slightly different than how we've done derivatives before, but it's part of this process. Right? We want to get dx by itself. So what we're going to do is we're essentially, and normally we don't write this part down, but I'm going to write it down this time. We're essentially multiplying both sides by 1 over 4x minus 3 just to get the dx part by itself. Really what's happening is you're taking whatever's over here and you're just putting it in the denominator. That gives us dx is equal to 1 over 4x minus 3 du. So what's changed from here to here? So we now have a dx and we have a u. So we can take this guy and we can change it to the 7th root of u. And we can take the dx and replace it with 1 over 4x minus 3 du. Notice then that this 4x minus 3 and this 4x minus 3 will cancel. What we are left with is a u to the, I'm just going to write 1/7 power, du. You add 1 to 1/7, you get 8/7. So this will be 7/8, and then replacing u with what it was originally. So your process is identifying a u, taking the derivative of both sides, solving to get dx by itself, and then plugging in u and dx to the original. So u goes in for the 2x squared minus 3x plus 5. This dx becomes this whole thing. All the x's should cancel. And then you integrate when you have u's. Once it's just down to the u's, you integrate, and then at the very end you plug your whatever u was back in. I want to try it with this next one. So we had already said, this is what was on the previous page of good choices of u. We already said that u would be equal to cosine y minus 3. What would my next step do? I want to kind of do this one together. What is my next step going to look like? Remembering this is y's instead of x's. So instead of like a dx, there's going to be like a dy. Take derivative both sides. So I get du is equal to what? Du is equal to negative sine y. And then what else? What else goes here? A dy. I hear a dy. It's a dy. Now, once again, when you go to get dy by itself, it works out a little. Some people don't do it the way that I do it, where I make it into a fraction over here. But I find it works a little easier. To get the dy by itself, I can do that without even really writing down any of the math. What would dy be equal to? There's going to be a du over here. What would dy be equal to? One over negative sine y, exactly. So it's really just whatever you had here, 1 over that. So you're just, yeah, exactly. You're dividing by negative sine y. I want you to make that substitution, all right? I'm going to give you, I don't know, I'm going to give you like 2.5 minutes. We've done this part here, all right? So what's left to do is this dy can be replaced with this. You're going to replace your cosine y minus 3 with u. Make those replacements, finish the substitution, and see what you get. All right, I'm going to give 2.5 minutes for that. All right, so I know this is kind of a weird one because it's not like because the power is kind of weird, but how are things looking right now? Maybe, all right, I'll take that. So you'll have this sine y here. Now it's going to be a u raised to the pi. And then the dy becomes 1 over negative sine y du. So the sine y's cancel, but there is a negative. This negative down here does need to come out. So I'm going to write this as negative u to the pi du. When I integrate, so adding 1 to pi is pi plus 1, so it's kind of gross. Negative 1 over pi plus 1, u to the pi plus 1 plus c. And then replacing u with cosine y minus 3 raised to the pi plus 1 plus c. Got it. All right. Excellent. Excellent. Anyone else? How did that one look? How did that one feel? I'll take a pretty good. This was actually like, I'd say a little bit more complicated. Especially because it's not a nice power. So let's actually take it to the examples on the next page. Like I said, the hardest part of this is going to be choosing your U. If you're looking at this problem here, we have a radical, we have some powers and stuff. What are we thinking should be our U here? I hear a 2t plus 3. That sounds like a good choice to me. Try 2t plus 3. I'm going to give you, I don't know, let's say 4 minutes to do this one. Try this guy out. Try using 2t plus 3 as your U and try doing the rest of it and see how that goes. I might slowly fill it in. I think I'm going to set a 4-minute timer and then I'm going to start slowly filling it in once I get down to like 1 minute left or maybe 2 minutes left. I'm going to start slowly filling it in along the way without saying anything, just so you can kind of glance up and check that you're on the right path. But I'm going to give you a good head start first. So I'm going to pause it and do that. All right, so I have kind of started this problem. Was everybody able to get up to this point here? Okay, excellent, excellent. Great. I'm going to pull that 1/2 out, and then I'm going to rewrite this as u to the negative 3/2 du. When I integrate, so I'm going to add 1 to negative 3/2. That's negative 1/2 u to the negative 1/2 plus c. Now, when you flip this ends up being 1/2 times negative 2, because if you 1 over negative 1/2 is 2 over negative 1, which is negative 2. U to the negative 1/2 plus c. That just comes out to be a negative because the 2's cancel. And then u is 2t plus 3 raised to the negative 1/2 plus c. How did that one come out for everybody? Pretty close? Pretty close. Was it the fraction stuff? It's always the fractions. Always the fraction stuff. Yeah, so sometimes, just take your time on it, um, however many steps you need to get the fraction stuff down. But were you able to get most of what happened? Like, was it mostly just out here that it was off? Okay, good, good. So the next one is kind of similar to this. And I feel like I can give you guys the opportunity to try this one on your own without me saying much. So I think what I'll do, again, I'm going to set a 4-minute timer. And then as I get towards the end of the timer, I'm going to start working through parts of the problem so that you're able to start checking your work. But I won't say anything until the entire 4-minute timer is gone. So let's try again. Let's do it with this problem down here. And I'm going to let you choose you. I'm going to let you be the decider there. All right, I'm going to set a 4-minute timer. Right, how is this one coming along? I've put up the first few steps of it. Pretty good. Okay, good, good, excellent. We were able to get that right choice of you in there. Excellent, excellent. So I've gone ahead and pulled out the 1/4, and then adding 1 to 3 halves, or to 1/2, you get 3 halves. U to the 3 halves plus C. This will turn into 1/4 times 2/3. And then we have y to the 4th plus 2 raised to the 3 halves plus C, which can be simplified into, let's see, 1/6. Yeah, 1/6. Y to the 4th plus 2 raised to the 3 halves plus C. Did that come out? How did that look? Because the process is, it's not that much different than what you've been doing. There's this additional step. So I do well up until the second to last step. Oh, is it the step right here with the fraction, the fraction bit? Fractions, always fractions. Just try to take it slow, if you need to, like, I like to kind of skip around. Like, I'll go from this step down to like having a 2/3, but take your time and feel free to use your calculator to do 1/4 times 2/3, but feel free to take the time. The fraction part is definitely going to be the hardest part. So just make sure you're step by step. Use your calculator if you need to. Feel free to, you can even, once you get to this step here, do it as 2/12 and then reduce it to 1/6. The first time you write the plus c. Then that would be what I would practice then. You could I would practice just, regular integration. Don't worry about the u substitution part. Just try a few more problems that have fractions in the exponents. Practice that. Make sure you're getting those steps down. Khan Academy is a good resource for that. Like if you want to do a lot of practice problems, because you have to get that part before you're able to, finish up the u substitution part. Excellent. So I know we just kind of have opened the lid on this box of u substitution, but I want to stay good to my word and keep today a lighter day. We're going to go through more examples of this on Monday, and we're going to expand upon it. In the meantime, I'm going to try to get these tests graded. Once the tests are graded and posted, I will make an announcement about when we'll be doing the session where you can come in and ask questions about the test. I'll make an announcement about all of that, and that'll be that. So if you would like to, practice more, there's more practice problems in this section. If you want to go ahead and try doing those before we have class on Monday, then you're going to be able to compare your work on Monday. So if you go through and do, a few of these, if you look through and see ones that look interesting, you can try a few of those out. There's also ones in the textbook. There's ones on Khan Academy. You can look up u substitution worksheets online, free u substitution worksheets. That'd be a good thing if you have some time right now to work on that. But I am going to keep today's lecture short. I'm going to cut it, 40 minutes short today, and say enjoy your Thanksgiving. No homework due this week. I'll try to get the exams graded so that you have those grades. But other than that, there's nothing due for quite some time. All right. Happy Thanksgiving. Thank you guys all for being here today on the Wednesday before Thanksgiving. Have a fantastic day.